Grounding and bonding are essential for electrical safety and equipment protection. Let's examine a situation involving grounding issues at a television station. The station has a 225 kV transformer stepping down 480 volts to 120/208 volts, three-phase. This transformer feeds a main distribution panel, or MDP, located in the same room. From the MDP, 5 200-amp feeders installed in electrical metallic tubing supply power to panels in the computer room. The computer room contains 6 cable trays positioned above the computers. The grounding electrode conductor, or GEC, for the transformer connects to a copper plate mounted on the wall. From this plate, the GEC extends to the building steel. Also connected to this copper plate are 6 bonding or grounding wires that run to the 6 cable trays, and 4 wires that connect to 4 panels terminating on an isolated ground bar. The 5th panel has an isolated ground bar with the ground wire connected to the building steel. In terms of the cable trays, metal-clad cable was initially used to wire isolated ground receptacles. However, since metal-clad cable is not suitable for isolated ground receptacles, the original contractor added a ground lug and wire in the panel, connecting it to a lug on the cable tray, stating that this would ground all the boxes. The recommended approach involves running an isolated ground wire from the transformer's XO terminal to the MDP, then distributing it with the feeders to the panels. Also, the metal-clad cable should not be used for isolated ground receptacles, and the wiring should be replaced. Firstly, let's discuss the acceptability of the bonding or grounding wires running from the copper plate to the cable trays. These wires can be considered acceptable as bonding wires, but there are a few points to address. Secondly, the GEC for the transformer should directly terminate to the building steel, bypassing the intermediate copper plate. Thirdly, the bonding wires should be appropriately sized to handle the potential fault current. In addition, it is best to use solid copper conductors for bonding. Fourthly, the use of metal-clad cable for isolated ground receptacles is not permitted. A separate grounding conductor must be run from the panel to the receptacle box. The ground lug and wire installed by the original contractor might not be sufficient. Now, let's explore the recommended modifications. 1. Terminate the GEC directly to the building steel. 2. Verify the size and material of the bonding wires and upgrade them if necessary. 3. Remove the metal-clad cable and install separate grounding conductors for all isolated ground receptacles. 4. Consider running the isolated ground wire from the transformer's XO terminal to the MDP, as this will provide a proper ground path for all downstream equipment. Here are some additional considerations. The grounding system should undergo thorough testing to ensure its effectiveness. All modifications should be carried out by a qualified electrician following the applicable electrical codes and standards. Regular maintenance and inspections are crucial for maintaining the integrity of the grounding system. It is important to understand the principles behind grounding and bonding. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. Bonding ensures that all metallic parts of an electrical system are at the same potential, minimizing the risk of electric shock. In this specific case, the copper plate acts as a common bonding point for the cable trays and panels. However, it is not the ideal location for the GEC termination. The GEC should always have a direct connection to the building steel or a ground rod, providing a direct path to earth. The size of the bonding wires is critical because they must be able to handle the maximum fault current that could occur. The National Electrical Code, or NEC, provides guidance on sizing grounding and bonding conductors based on the size of the service entrance conductors or the feeder conductors. The NEC also specifies the requirements for isolated ground systems. Isolated ground receptacles are designed to reduce electrical noise and interference, which is particularly important for sensitive electronic equipment like computers and audio/video equipment. The isolated ground conductor must be run separately from the equipment grounding conductor and must terminate at the isolated ground bus in the panel. The isolated ground bus must be connected to the grounding electrode system. The use of metal-clad cable for isolated ground receptacles is not permitted because the metal sheath of the cable can introduce noise into the isolated ground system. A separate insulated grounding conductor must be run with the circuit conductors. When installing isolated ground receptacles, it is important to follow the manufacturer's instructions and the requirements of the NEC. The receptacles should be clearly marked as isolated ground receptacles. The grounding system should be tested regularly to ensure that it is functioning properly. Testing should include measuring the ground impedance and verifying the continuity of the grounding conductors. The grounding system should also be inspected for any signs of damage or corrosion. If any problems are found, they should be corrected immediately. By following these recommendations, the television station can improve the safety and reliability of its electrical system and protect its sensitive electronic equipment. The location of the copper plate and its use as a central grounding point raises some concerns about potential ground loops. A ground loop occurs when there are multiple paths for ground current to flow, which can create circulating currents that cause noise and interference. To minimize the risk of ground loops, it is important to ensure that there is only one path for ground current to flow. This can be achieved by using a star grounding configuration, where all grounding conductors are connected to a single grounding point. In this case, the ideal grounding point would be the building steel or a ground rod. The copper plate should be eliminated as a grounding point, and all grounding conductors should be connected directly to the building steel or ground rod. Another potential issue is the connection of the isolated ground wires to the building steel in the fifth panel. This defeats the purpose of the isolated ground system, which is to isolate the equipment from the noise and interference present on the building ground. The isolated ground wire should be run directly to the isolated ground bus in the panel and should not be connected to the building steel. The use of metal-clad cable for isolated ground receptacles is a common mistake. Metal-clad cable is designed for general-purpose wiring and is not suitable for isolated ground circuits. The metal sheath of the cable can act as an antenna, picking up noise and interference and transmitting it to the isolated ground system. In addition, the metal sheath can create a ground loop if it is connected to both the equipment grounding conductor and the isolated ground conductor. To correct this problem, the metal-clad cable should be replaced with a cable that is specifically designed for isolated ground circuits. This type of cable has a separate insulated grounding conductor that is isolated from the metal sheath. When replacing the metal-clad cable, it is important to ensure that the new cable is properly supported and protected. The cable should be run in conduit or cable tray, and it should be protected from physical damage. The connections to the receptacles and the panel should be made with approved connectors. The grounding system should be tested after the modifications are complete to ensure that it is functioning properly. The testing should include measuring the ground impedance and verifying the continuity of the grounding conductors. The grounding system should also be inspected for any signs of damage or corrosion. If any problems are found, they should be corrected immediately. In addition to the specific recommendations outlined above, there are some general best practices for grounding and bonding that should be followed. All grounding and bonding connections should be clean and tight. Corrosion can increase the resistance of the connections and reduce their effectiveness. All grounding and bonding conductors should be properly sized. The size of the conductors should be based on the size of the service entrance conductors or the feeder conductors, as specified in the NEC. All grounding and bonding conductors should be protected from physical damage. The conductors should be run in conduit or cable tray, and they should be supported properly. The grounding system should be inspected regularly. The inspection should include checking the connections for corrosion and tightness, and verifying the continuity of the grounding conductors. Any problems that are found should be corrected immediately. The NEC provides detailed requirements for grounding and bonding. It is important to consult the NEC when designing and installing a grounding system. The NEC also provides guidance on the inspection and maintenance of grounding systems. Understanding the principles of grounding and bonding is essential for electrical safety and equipment protection. By following the recommendations outlined above, the television station can improve the safety and reliability of its electrical system and protect its sensitive electronic equipment. Regular maintenance and inspection of the grounding system are critical to ensure its continued effectiveness. A properly designed and maintained grounding system is an essential component of any electrical system, especially in environments with sensitive electronic equipment. The grounding system must be thoroughly tested to verify its effectiveness. This testing should include impedance measurements and continuity checks. All modifications should be performed by a qualified electrician in accordance with applicable electrical codes and standards, such as the NEC. By implementing these changes, the TV station can ensure a safer and more reliable electrical system, protecting its valuable equipment from damage due to electrical faults or surges, and minimizing the risk of electrical shock to personnel. Furthermore, a clean and well-maintained grounding system will contribute to a reduction in electrical noise and interference, leading to improved performance of the sensitive electronic equipment in the computer room. The importance of proper grounding and bonding cannot be overstated. It is a fundamental aspect of electrical safety and equipment protection. By understanding the principles and following the recommendations, you can ensure a safe and reliable electrical system for your facility. When dealing with grounding issues, it is always recommended to consult with a qualified electrical engineer or electrician who has experience in grounding and bonding. They can assess the specific situation and provide tailored recommendations to address the specific needs of the facility. Remember, electrical safety is paramount, and proper grounding and bonding are essential components of a safe electrical system. By taking the necessary steps to ensure a proper grounding system, you can protect your employees, your equipment, and your facility from the hazards of electricity. This information is intended for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer for specific recommendations related to your situation.